just cut the beginning part out.
Okay, you can start.
So let's look at a variety of polar curves to see what we mean by these components and how we can look. We're gonna. It's okay. Don't. Okay. How do I start this?
Wait, hold on.
It's not like choose that moment. You don't have to stop recording. It's okay.
It's still going.
Okay. Okay. Let's look at these 4 different polar curves to see what we mean by those. No, that's not it. Okay. Let's look at these 4 polar curves to find the. Nope.
Do you want me to stop it?
That's okay. I'm trying to find the wrong. Okay, let's just look at some examples of polar curves. So as you can see in these examples I've chosen, 2 of them have sine as the actual function, 2 of them have cosine as the actual function, 2 of them have the plus in the middle, and 2 of them have the minus in the middle. As well as 2 of them have a greater a value, these 2 have greater a values, and these 2 have greater b values. So all these differences add up, and we can see them, we'll see it in these 4 graphs. So for the first one, 2 plus 5 sine theta. So here's the graph of 2 plus 5 sine theta, and as you can see, the length of the loop is 3. And we know that the length of the loop is 3 because the difference between b and a is 3, which indicates that the loop is 3. Second thing, the length of the whole thing, the length of the big thing from the top to the origin is 7. And we know this because a plus b, 2 plus 5 is 7. So that's how we got that. Notice how this curve goes up. And because it's on the sine, it's a sine function, it should be symmetrical to the y-axis, and it goes up. And we know this because it's a plus here, there's a plus in the middle, which means it's on the positive part of the axis. And as you know, you should have already told by now, because a is less than b, this is a loop limit zone. And this is another example of the loop limit zone. It's looped because, again, a is less than b. But this time there's a minus in the middle instead of a plus, which means it's going to be going on the negative part. So this, because there's a cosine here, this loop limit zone is symmetric across the x-axis. And because it's negative, it's going to be on the negative part of the x-axis, which means it's going this way. And then the length is 7, as you can tell, 2 plus 5 is 7, a plus b, and then the length of the loop is 3, because the difference between b and a, 5 and 2, is 3. And that's how we got that graph. Now let's look at these dimpled limit zones. So for the dimpled one, a is 5 and b is 2. And the plus, there's a plus sign here, and there's a cosine function. So because it's a cosine function, we know that it's going to be symmetric across the x-axis, and we can see that here. And because there's a plus in the middle, it's going to be on the positive part of the x-axis, which is why most of it is going to the right. And then if we look at the a and b values for the length of the limit zone, 5 plus 2 is 7, right? So that's why we have from the origin to the end of the limit zone, the dimpled limit zone, that's 7. And then for the dimpled part, this back part, is the dimpled part. We know that the length of the dimple is going to be the difference between a and b, which in this case is 5 and 2 would be 3. The difference between 5 and 2 is 3, which is why the length of the dimple is 3. And then for the last one, a last dimpled limit zone, the difference is that there's a sine function and that there's a minus in the middle. So because it's a sine function, this limit zone is symmetrical across the y-axis. And we can see that here. And because there's a minus in the middle, it's going to be on the negative side of the y-axis, which is why most of it goes down here. So again, the length of the limit zone from the origin to the end is going to be a plus b, 5 plus 2, 7, which is why this whole thing is 7, as you can see here. And the length of the dimple, this back part, is going to be the difference between 5 and 2, the difference between a and b, sorry, which is the difference between 5 and 2, which is 3, and this is why you see it here. So these are some examples with a lot of variations, and hopefully with these components and with these predictions that you can get from the graph and the equation, you can figure out how your graph would look.